Welcome to Web Handling. My name is Dave Roysum. I will be your guide on an exploration of what we know and what we don't know about overspeed in web handling applications. I know your time is precious, so let's get started. Overspeed is essential for many forming and converting processes. For example, coder types such as curtain, forward and reverse roll coders, as well as smoothing and metering methods such as Meyer rods, all have elements that are running at speeds quite different than the web. In extrusion, the melt speed is different than the web speed. As with curtain coating, the final coat weight can be made much thinner than the curtain because the web typically moves faster. In the paper-making head box, the speed of the pulp as it is laid onto the wire can be varied from slightly faster to slightly slower to change the fiber orientation and anisotropy. We use droop and some drive control methods when running stiff webs. Here, the motor is nominally in draw or speed control, but the gain is very low. Thus, the speed difference command set by the operator is more of a suggestion. What really happens is that the drive is running in a hybrid of speed and torque control. Overspeed is also used in most motor-clutch combinations. Here, a cheap motor travels at a simple fixed speed somewhat faster than the web. Torque control is achieved by the setting of the electric, magnetic particle, or pneumatic clutch. In this presentation, however, we will focus on a subset of overspeed applications that are used in web handling rather than web converting or web forming. Here, the motor or brake is turning substantially different than web speed. Here, the motor is not directly coupled to the web. The web handling applications we will discuss here includes accumulators, slitting, trim handling, tendency drives, and slip core winding. The accumulator is a series of top and bottom rollers that serve as a buffer between a steady-state process and a winder or unwind that must stop for roll change. The accumulator is an alternative to stopping the process for roll change or using an expensive turret winder or unwind. Most of the time, the accumulator is in a run state. At that time, it serves as a tension control element, very much like a dancer. Most of the time, the carriage is in a filled or unfilled position. The unfilled position is in the latter part of the roll change time, but can be also used during run to make the accumulator slightly less wrinkle prone by reducing span lengths and then filling the accumulator at the last possible minute before the roll change. There are many challenges with accumulators such as alignment, wrinkling, and tension upsets. These and others have been well documented by Neil Michael and others at the last couple of iWeb conferences. Sizing an accumulator is by far the most straightforward of any overspeed application in web handling. You first need to determine how much time you need for roll change. Next, you need to size the accumulator storage. Here it is a matter of deciding whether you want only a few rollers with a long span, which may be cheaper but more wrinkle prone and may not fit under some ceilings, or more rollers with a short span which have more maintenance. Simple sizing does not imply simple or trouble-free mechanics, however. We are just beginning to understand the dynamics of the accumulator and have not even begun to incorporate that into drive modeling. More importantly, the real-world mechanical and electrical problems can be formidable. Slitting is the most common of converting operations. Billions of blades have been in service. However, common does not necessarily mean well understood. Most of what we know about slitting is as a craft rather than as a science. In the case of the tangential slitters, sometimes the bottom band is driven. If so, it should be driven slightly or somewhat faster than web speed. The reasons are due to the sloppiness of the drive, the need for additional breakaway torque, and due to geometrical effective tip speeds. First, we might make an assumption or presumption that the component of the speed of the top blade in the direction of web travel must be equal to or greater than web speed. This is not strictly true. Recall from your personal experience how some webs can be cut with extremely sharp scissors without snipping. However, if we make this conservative assumption, then we can calculate from trigonometry the bottom band speed needed to do this. The table given here is from the venerable Blade Runners seminar given by Reinhold Schabel. The previous theoretical considerations are merely a starting point. Experience is even more valuable a teacher. Here, experience has shown that overspeed should be in the 1 to 100% range, depending on the web material to be cut. That, to put it mildly, is quite a range. So, given experience, how do we actually program drives in the real world? The previous tables and things like it indicate a simple percent may be desirable, and that is how geared drives work. However, in the real world, that may not work well for independent motor drives. The reason is that we need a breakaway torque at low speeds. Thus, an offset may be better, and in fact is often what is done with AC scalar motors. So now, with the simplest and most common of converting elements, we have some considerable variation for overspeed recommendations based on theoretical, mechanical, and electrical realities. Vacuum is a common way to remove trim from a slitting operation. An airspeed greater than web trim speed generates the necessary tension to handle the trim. It must never be below web speed, else the trim system will plug immediately. However, if the tension is too high, it is common to cause the trim to be unstable on some materials such as paper. Since rewinder speeds vary from 0 to thread speed to full speed, it is often a good idea to program the vacuum blower speed to vary with winder speed. As with most overspeed applications, there is little science but a ton of experience to guide design. The following are used by QuickDraft. The first thing to note is whether you have a light material, in which case you will have trim speeds approximately 50% faster than web speed, or heavy materials, in which case the recommendation is entirely different and is based on having twice the air mass flow rate as material mass flow rate. To this, we have many other quite important details that affect design, including material stiffness. However, the most important other detail is for a minimum airspeed of 4,500 feet per minute or 1,500 meters per minute, no matter what. This slide shows the example calculations typical of a high-speed paper winder. However, there are at least 3 guidelines I have found for trim airspeeds, all from the same industry, but all slightly different. This one was from the Winder Engineering Application and Design books from the former Beloit Corporation. It is similar, but more conservative in some places and more nebulous in others than what we saw with QuickDraft. From a similar era in a similar industry, we have yet another set of recommendations. While they show similar concerns for light and heavy materials in that airspeed and air mass, respectively, are important, the numbers are again a bit different. Slip core differential shaft winding is used on many small duplex winders, especially when the material is incompressible. This would include some papers, most film, and all foil. Shown here is the core lock option, though core slip and side load options have similar issues that we will discuss next. Recommendations for differential shaft overspeed are almost non-existent in the literature and hard to get from the suppliers. This causes no end of trouble for customers who don't know how to set the speeds. Furthermore, some literature recommends a slope and other an offset that is harder to do with drives of all types. If the specific value of overspeed didn't matter, we wouldn't be concerned. However, as it turns out, it matters a lot. The concerns are more serious than with other overspeeds and are similar to what we have with tendency drives that we will cover next. The tendency drive is a poor man's helper drive. By this, I mean it would be desirable to counter bearing drag and inertia. This can be a concern for lightweight webs and lightly wrapped rollers, either of which could cause the web to slip on the rollers. The classic application is for arched ovens, though there are others. In any case, the motor overspeed tends to turn the torque on the live shaft roller. Ideally, the positive torque from the roller bearings would exactly counter the drag from the live shaft support. This, obviously, will never happen exactly, and even if it were close enough, there is not compensation for inertia during speed changes. Thus, it is a poor man's attempt at a true helper drive, where a precisely tuned motor would be connected to each roller. Instead of looking at drag, let's use the effective coefficient of friction of the bearing. As we can see with this figure, the drag depends greatly on many factors, including speed, as the system moves into different regimes of lubrication. Another look at bearing drag shows an empirical approach that first begins by considering design and load. To these we add torque due to viscous lubricants. To do this, we need to know temperature, viscosity, speed, and other parameters. The bottom line is complexity far beyond what most design engineers would ever want to deal with. Now consider the plant engineer, or worse yet, the operator, who must deal with this complexity. The big picture problem with both slip core and tendency drives is complexity. The amount of tension produced on the web or winding roll depends on so many factors, almost none of which will be known by the engineers who built the machine, much less the poor operator who must operate the machine. Worse yet is the design sin of having two knobs to do the same thing, as is the case in overspeed and pressure on differential shafts. I hope this presentation has inspired questions. I hope even more to inspire research to find answers on how to best deal with the many types of overspeed in the even many more types of applications.